And thank you for joining us today for the Bicentennial Alliance Lecture Series. My name is Melanie Keeney, and I am the Director of Engagement and Outreach here at Missouri S&T, and today I will serve as your host and moderator. Missouri S&T is currently celebrating its 150th anniversary, coinciding with the Missouri Bicentennial celebration. As a way to honor Missouri's bicentennial, S&T is hosting a lecture series titled Honoring Our Past, Envisioning the Future, Missouri S&T's lecture series for the bicentennial. The series celebrates the rich cultural history of our region and explores social and economic growth topics relative to Missourians. Today, we present the third in this series titled Having a Blast with Explosives. Before we get started, I'd like to go over a couple things. First, today's speaker will welcome your questions. If you have a question that you would like to ask, please put it into the Q&A box. The chat function is disabled during this presentation, so all questions will need to go into that Q&A box. Feel free to go ahead and put those questions into that box as Dr. Johnson is speaking, and I will collect those questions, and once we get to the Q&A session, I'll be able to start asking those. As a thank you for participating in today's presentation, we will be doing a raffle. The raffle will include a gift bag, and inside this gift bag will be Missouri S&T 150th anniversary branded giveaways, as well as Missouri Bicentennial branded giveaways. And it will also include a copy of Dr. Larry Gregg's book, Forged in Gold. And for that drawing, we will randomly select that winner and announce it at the end of today's presentation. And then we will get with that winner to deliver them or set up for a pickup for them to pick up their prize. With that, I'd like to welcome our speaker. Today's speaker is Dr. Catherine Johnson. She is the Assistant Professor of Explosives Engineering here at Missouri S&T. Dr. Johnson's research interests include explosive propagation in air, shock physics, fragmentation prediction, environmental considerations of blast, and the advancement of blasting practices and technology. With that, Dr. Johnson, I turn this over to you.
Thanks, Melanie, and thank you everyone for joining this afternoon and listening to my talk. Let me share my screen, the correct one. Here we go. So hopefully you can see my screen. And again, thank you for joining me today. My name is Catherine Johnson. I've been here since 2015. My background was from the University of Kentucky, where I got my PhD. And then before that, the University of Leeds, where I got my bachelor's and master's. All of those degrees were in mining engineering. And since I joined Missouri S&T, more of my research has been to do with the military high explosive side of things. My goal today is to get across a little bit how we take a lot of people's dream job as a kid and turn that into patents, papers, and research projects and student graduation, hopefully. So as we move forward, I wanted to start and talk a little bit about the history of explosives at Missouri S&T and, of course, UMR and Missouri School of Mines before that. So if we overlay some of the explosives history over this, we can kind of see that the Missouri School of Mines was founded right around the time of the dynamite and initial blast and cap or detonator inventions in the 60s. That detonator is still very similar to the detonators that we use today, and dynamite is still used. We still use it out of our mine occasionally, and actually the only dynamite plant left in the US is here in Missouri, about an hour and a half from Rolla. As we go a bit further into that history, in the 50s, we've got ammonium nitrate with fuel oil that was invented, and emulsion not long after that, when we were able to use that ammonium nitrate in water environments and wet environments. One part of this that I did want to draw attention to was 1984 with electronic detonators being invented. That was the early work in that, and one of the early patents was a colleague or recent colleague of mine, recently retired Professor Ozzie. So we do have a pretty strong part of overall explosive history that comes from UMR at that time. As we developed the explosives program out of the mining engineering program. We have some pretty unique facilities, which the main one being our experimental mine, which was opened back in, or we acquired it back in 1913. And we have both underground and surface facilities that we still use regularly. And I'll show you some videos today of some testing that we do at both of those locations. Most recently, in 2016, we did open the Kennedy Mine building. That expanded our capabilities a lot with regard to student teaching and education, with new classrooms, new labs, and really changed what we can do there. And then finally, got the actual explosives program and work that we've done related to that added in here. So even though we've used explosives since almost the beginning of Missouri School of Mines, it's only recently that we've had official degrees in explosives engineering. In 2014, which was right before I joined, and a big reason that they added additional faculty and thankfully me to join here was that explosives PhD program. 2014 is the only PhD program of its type that I know of anyway. And then 2010, right before that, we had the explosives masters. And we now are looking at over 100 master's graduates that we have dotted around the country and world. So moving on from that and talking a little bit about explosives in the US, there are a lot of them that are used, over 7 billion pounds annually, and over 90% of those used in mining or rock blasting. That really was the start of everything that I did with regard to research. But what I want to talk about today are those remaining uses and those things we don't necessarily think about and know about, and how we utilize the facilities and capabilities that have been grown and developed over the last 150 years into novel new research. So there were many topics that I could have chose today, and I ended up deciding on fighter jet canopy ejection, traumatic brain injury mitigation, coal dust explosion suppression, and detonation synthesis. So if we start with fighter jet canopy ejection, this really was a project that stemmed from students taking a class and intrigue and discussion around this area, and it resulted in us just going out and doing some testing and trying to figure out the answers to our debate rather than just still discussing them. Before I talk more about canopy ejection, I wanted to talk a little bit about some of the first uses of explosives in aircraft. You can see here this little video playing of explosively formed rivets. I included this in here. They've got a really small amount of explosive that with that heat is going to react and expand that rivet. I included this because I think it's a great example of, right here, prevented tool marks and accidental damage to aircraft surfaces during manufacture. I think it's great that something that is normally associated with damage and destruction actually causing less damage and destruction than other more conventional manufacturing means. But going back to what I was actually going to talk about a little bit, fighter jet canopy ejection. We use explosives in two ways for this, or energetics, I should say. We use high explosives to actually remove the canopy, and then we use rocket propellant to eject the pilot. We need to do this pretty quickly, and that's why explosives are the main use for this. They do react rapidly and quickly, and it's typically done in under 10 milliseconds. So talking specifically about the canopy removal, the explosives that we use for that is a mild detonating cord. This is literally a cord with a plastic coating on it that contains one of two explosives, typically PETN or HMX. It travels, if you initiate it at one end, it travels at about 21,000 feet per second. from one end to the other, and a very consistent velocity. Comes in a whole sorts of, we refer to it as grains per foot, at least here in America anyway, rather than meters per second, pounds per or grams per meter or something like that. But it ranges from 5 to 250 plus grains per foot. But the mild stuff that we've got in these canopies close to a pilot is typically less than 15 grains per foot that we're talking about. So as some of my students here, tying some together, so long as you tie it either parallel or perpendicular to prevent cutoffs, you can use one initiator and initiate an awful lot of this in different patterns and designs, and they use it in mining and blasting to initiate different blast holes. They use it in the military for breaching applications, and here obviously we're talking about it for its use in canopy ejection. So some of the current research, not just within my group, but in general, to do with this is changing the overall design to distribute that detonating cord throughout the canopy. Some of the early designs, you can somewhat faintly see here, just line around the outside of that, and it would break as one and move away. More recently, you can see vaguely here the detonating cord is in different patterns throughout that canopy, so it breaks into smaller pieces. I don't know if there's any Top Gun fans out there, but some of these newer designs would result in hopefully a better outcome for Goose. And that's not just a movie that I enjoy watching and especially enjoying the music, but it really is a problem that exists in the for fighter jet pilots, and there's research going into obviously improving that. The other main research area is looking at dual channels for detonating cord. So rather than one larger cord, having two parallel cords next to each other, and improvements for that. So looking specifically at these designs and changes, you can see here, this is actually the Red Arrows, the British acrobatic team. It's Hawk from BAE Systems, and you can see this, what I call sort of heartbeat design. I don't know if that's actually what it's called, but that's what I call it. And rather than a straight line that would cause a straight crack between there and one piece, these two areas with directional energy towards each other are supposed to create a crack between them, meaning this would break into three smaller pieces rather than one larger one. And obviously having smaller pieces to move and not have large pieces there as the pilot is exiting. The one that really got me and was the big debate within my group was the dual detonating cord theory, where they say that shockwave interaction is going to define the fracture plane between the parallel cords of detonating cord. So if you're looking at the profile of this, you can see here the images show that there should be a fracture plane between them where you have overlapping energy from both lines. My PhD actually looked at shock collision in rock for blasting applications and fragmentation, and I determined there that it wasn't that was causing the fragmentation, and I felt quite strongly with my research team when discussing that I didn't believe that this is the way that it was breaking. So. We go out to the experimental mine, we do some testing. So this is me and some of my grad students connecting this line at the bottom is just our initiating cord, basically, so that we could try and get the timing of these lines as perfect as we can. You can see on the right, we've got two parallel lines, so this should break all as one. And on the left, we have got that sort of heartbeat design that should break this into 5 distinct sections. On the top, you can see that there's two parallel lines, and at the bottom is one line. The bottom single line is 15 grain per foot mild detonating cord, and the two lines are our 7.5 grain per foot each, so equivalent explosive mass that we're using in each of those designs. So videos, you'll realize today that really the reason I picked some of these topics is because I get enjoyment still of watching the high-speed video footage of us recording these. We recorded this video at 55,000 frames per second, and I'm going to play this one back 65 times slower than real time. So you can see that we are, and the camera is in a bunker protected, but you can see really clearly here those 5 distinct separated areas compared to one full area on the other side. And that was the dual chord system. If we play these again side by side, this one is played back slower. So this is 2,500 times slower than real speed, and you can really see and look in between and see some of the shock traveling through this plexiglass as we go through. And you can also see the difference in there's quite a lot of or extensive fireball from the higher grain per foot initiating chord that we're using compared to the lower mild detonating chord within the actual canopy. Doesn't get old. And then finally a side-on view. This is a color camera, and again, a lot of the fireball is coming from that detonating chord at the bottom that we're using to initiate, but you can see those pieces and the velocity that they fly out. And it's this piece here that's my favorite bit. So this are results afterwards. This is that sort of heartbeat design and pattern that's actually the area between those parallel lines of 7.5 grain per foot detonating chord that this was supposed to, in theory, crack right down between. And we, have that piece that I am smiling holding. I do like being correct occasionally. So this was fun to actually see the results and actually, in a relatively short amount of time from the discussion, turn this around into reality and really try to understand what's happening here. And then on the left, we've got a student of mine, Cody, and you can really clearly see that straight line crack from one side compared to this clear design from the other, and how precise that detonating chord is in cracking and separating that canopy. So through this, we really can get a better understanding of shock physics and material interactions through fracture response. Whether it was for my PhD initially for rock blasting applications, or in this instance for canopy ejection, we have the facilities and capabilities to be able to do these kind of tests and provide a safer means for extreme circumstances like pilot ejection. Moving on a little bit to traumatic brain injury mitigation. This is a topic that I have been researching for the whole time that I've been here. And I'll talk a little bit about what we do and how we help this overall problem. Most of you probably heard of traumatic brain injury or concussion from some. There's 4 main types though we've got that are causing this. We've got a blast wave impacting the brain. Head acceleration can cause traumatic brain injury that you might associate with whiplash or a car incident. We have a thoracic injury that is impact to the chest and lung damage that then transfers up into the brain and causes TBI, or a penetrating injury. What we specifically look at within the explosive program, obviously, is the blast wave impacting the brain. It is difficult to have facilities to test this. There's a lot of tests that are done through shock tubes. And we are able to create a model that mimics military scenarios pretty well. And then we also have 3 severities: mild, moderate, and severe. And we're mainly looking at mild. The Mild TBI or mild blast-induced TBI is a signature wound of recent conflicts. It is difficult to diagnose. It's difficult to determine what extent or what magnitude of a blast is causing this, or whether it's multiple blasts that are causing this. And that's some of the things that we're looking into. If we look here, just sort of bring home again sort of why this is important, why we're doing this. DoD numbers there show over 80% of these cases are mild TBI cases. And CDC incident rates with traumatic brain injuries being a lot higher than a lot of other injuries that we research and look into a lot. And then I just have this news article here that you might remember from a year ago with over 100 US troops diagnosed with TBI following that Iran strike. Many of them were a long way away from that. And we want to look, and that was just one incident, one event. So we definitely want to be looking into this and figuring out what's going on and how we can mitigate it. What I do specifically is use high explosives in open air through quantities, and by changing the quantity and distance, we can change the pressure and impulse, which is our pressure over time or loading over time. That is resulted on our target. We monitor all of that. We use high-speed cameras and monitor the shock front coming in and outgoing. And then we work with neuroscientists across the country. And my biggest collaboration is with University of Missouri Columbia and also the Truman VA. And we collaborate on this area quite a lot. Going back to videos, this is, you'll see a flash from the explosive that's about 3 meters away. You'll see the shock front propagate through from the left, and what we're looking at there is compression of the air as it moves through, and we see a really dense change that we can visualize using a high-speed camera. One benefit, you can see this much clearer in the in humid air. So it's one of the few benefits of the Missouri summer, is that we can visualize this very well. So you can see the flash of the explosive, and you can see that shock front moving in through and interacting with that stand. Following it is a ground reflection as that moves through. But we look into the interaction with those objects, with other things, and we can determine what is reflected away compared to actually absorbed. And that's the difference, is what's actually absorbed that is what we need to look at, rather than what's measured on the outside or in air to determine what's really happening. Another aspect of this that we look into quite a bit is just non-uniform pressure distribution. We have simple calculations that relate quantity of your explosive charge to a safe distance that you can stand from that explosive charge. All of these formula, though, are based on uniform distribution of pressure, or a spherical charge that has energy going in 360 degrees. Most charges that are used for this example and picture of breaching applications is you don't have energy going in 360 degrees. You have much of it coming back in only 180 degrees, with some of that being absorbed into the structure. In addition, you don't have a spherical charge to breach through, so geometry and confinement are going to cause a large impact on what is happening here as well. So another video, you'll probably notice that really I chose these topics because of these videos, or I probably said that already too. But what we've got here is a sheet explosive. It's 6 inches by 6 inches by only 1/8 of an inch. So almost looking at a 2D explosive. And this one is 100 grams. It is initiated by a blasting cap, an electric blasting cap in the orientation of that arrow. So the initial energy is going in that orientation. And what you can see when this plays is how two-directional that is. We don't have much coming towards us, you know, looking at the screen here, but you also see a lot more in the direction of the initial initiation of that, and very much an ellipsoidal distribution of energy. If we look at that through a simulation, what I want to show here is this K18. This is a very typical value that they use and calculate to. It's around 3.5 psi equivalent, and that is what we're calculating based on uniform pressure distribution of where you can and should stand. If we play this, this is a sheet explosive on a hard surface. You can see again most of that energy coming in the initial orientation of the initiation, and at 0 degrees you end up still with a higher pressure than designed and safe to be. 45 degrees you are pretty much right at that safe threshold, but at 90 degrees have an additional safety factor in there. So some of the things that we're looking at is whether we can include simple additions to these basic formula that are more realistic now that we know how much of a problem blasting to TBI can be. And this is just static overpressure over time for those same orientations where we have a quick rise time. The rate of that rise also contributes to changes within the cells within the brain, but here at 0 we can see we're above that safe threshold, and 90 you can see again quite clearly that we're well below that safe threshold, and obviously a much better place to be. These explosives can also, these sheet-based explosives also be used for fun. I included this in here. This is a picture from Jacqueline Camp back in 2017, since I started working on this. And the guy in the middle won this explosively etched plate that we made. So in order to do that, we are cutting some sort of stencil. This one is cut with a water jet machine, so the stencil's out of brass, and we use that stencil in between sheet-based explosive. This is that same explosive that you saw in the high-speed video, as well as that simulation. And on the bottom we have a brass plate that we want to etch onto. So this area here is just where we want our blasting cap, so we don't want to damage the bottom of the plate too much, but wherever we have these holes and less resistance, I guess, for the energy distribution to go through, we end up etching that onto the plate. So this is one example of what that results in. What I like also about this is you can really well see the pressure distribution and energy distribution as that cap was initiated here, and you can see a lot of interactions that went on between those areas through that through those holes. And then this is another one. This is actually my belt buckle for my belt that I do pretty much all our testing in now. I gifted this to a student. It was one of the first ones we did, and we made a stencil out of, well, we 3D printed the stencil. And then within a week, he gifted it back to me as a belt buckle that I always use. So it's something that our team does quite a lot now, and has kind of been our giveaway as people come and visit and see us, and we like playing with figuring out how much detail we really can go into with these things. But moving back to my overview and the main topics I wanted to talk about, this next one is coal dust explosion suppression. This is a topic area that we're able to do because of facilities that have been developed over a number of years out of the experimental mine way before my time. We've got 2 underground portals. One is primarily used for student education, and they blast and expand that each year. And the other one is a research area that is an underground limestone mine that is we're able to use it for research like this. We call it the Wombat, and it was initially developed to use a water jet to demill old ammunition. and now I use it for coal dust explosion suppression research. This is an important topic. This here is some history of fatalities from coal mining, but we can see here we really are pretty low in recent years. The last big disaster we had was Upper Big Branch in 2010. And NIOSH, the National Institute of Occupational Safety and Health, have been putting quite a lot of money into research into explosion suppression since then. I put on here back going to my timelines that I like with Missouri School of Mines back on there again, and how important some of the research we did as Missouri School of Mines in reducing these incidents as we go through time. So how and why do we even need to, or how can we suppress a coal dust explosion? Most of what goes on at the moment in the US is reducing the ability for a coal dust explosion to occur in the first place. A coal dust explosion starts with, typically, with ignition of a small pocket of methane. We try and reduce those pockets by having ventilation, by monitoring the gas, and only using permissible systems that don't cause sparking and things like that. As that methane ignites, we disperse coal dust from the floor and walls, and it's that coal dust that is obviously throughout the whole mine that can propagate that high energy explosion throughout and cause the damage. So to prevent, if there was methane ignition, to prevent coal dust explosion propagating from that, we remove coal dust accumulations, we wet it so it can't become airborne. And we cover the walls and floors with rock dust to have an inert material there and cool down and stop the reaction propagating between fine dust particles of coal dust. A lot of places, including the UK, they require a barrier system by law, so does some areas of Australia and other areas in Europe, and they require some sort of barrier system, which is a last line of defense. It doesn't stop a coal dust explosion occurring, but it does suppress it if it did. And this is the area that NIOSH have been putting money into to see what's going to work for us. I've been fortunate enough to have two different projects related to this. On the left, you can see me and a couple of my students installing a passive type system that they call the bag barrier system. This was installed in a US coal mine in West Virginia, and the first barrier system that was installed. We did not do a full installation, but we were looking at whether it's even feasible or useful in the US. A lot of other areas that have coal mining have standardized mine heights, whereas we are mining to the height of the coal, and we have different ventilation systems as well. So it kind of took a somewhat cheap system into one that is more costly in the US than it is in other areas. And the way that it works is if you do have an explosion, the pressure front, I don't know if you noticed in any of the other videos that I've shown, the shock front travels much faster and leads the fireball. So the pressure front will pass through, it will rupture these bags that are filled with rock dust, and it will disperse all of that onto the floor and put out the fireball that is following it, and therefore preventing it from propagating further throughout the mine. So that was a project that was really looking at whether it was feasible. And the second project that we had looked at developing an active barrier system. So this is an active system that we prototyped and put together, and this is in the Wombat, in the portal out of the experimental mine. And the difference here is that this one's triggered from some sort of sensor that can be placed closer to the ignition source, whereas a passive system, you have to wait for the pressure front at least to get to the bags. An active system you can trigger much earlier, and we triggered it from a combination of 2 of 3 of heat, pressure, and light. So 2 of those 3 to not have a false trigger. The sensor is much closer to where that initial methane source would be, and then it's going to start dispersing. This is filled with typical fire extinguisher powder, ABC powder, and it was charged to about 200 psi with nitrogen gas to release that as soon as it's triggered before. And then this, you can see the roof mesh a little bit here at the top. So this is a GoPro that was just recording this video, and it was of, this is an unsuppressed coal dust explosion. That was our control test that we did underground at the Wombat. The heat through that is pretty intense, and the duration of that flame, and the camera did survive. We use those quite a lot and push them to their limits at times, but it really allows us, and being able to actually have a test facility that we can do full-scale tests in is unlike anywhere else. In the US, the government used to have a few test sites, but they've since been closed down, and that coal dust explosion was the first coal dust explosion in the US in an actual underground opening for several years. But it allows us to really start to understand the nature of dust explosion propagation and suppression, and see how these systems are going to work to mitigate risks associated with mining processes that we still need. And then the final one, detonation synthesis. This project and topic area really has stemmed from a collaboration between myself, ceramic engineering, Professor Fahrenholtz, and chemistry with Professor Machalin. And really it was a conversation by accident and realizing interests and capabilities, and now we have developed and built custom chambers to do this sort of work here at S&T. So what we can actually do is we're looking at the products of detonation to determine and change how we are manufacturing and detonating these explosives to have different detonation products. If you have an ideal detonation, you have nitrogen gas, you have H2O in the form of hot steam, and you have CO2. If you change that away from a perfectly oxygen balanced explosive, we can start to get typically carbon by itself, and then we also are trying to react the nitrogen as well to form other things. And we use obviously the pretty extreme temperatures and pressures of an explosion to be able to do that. And the main things that we're looking at trying to make silicon carbide and boron nitride at the moment. So how do we actually do this? We have got a blast chamber. We obviously need to collect these detonation products. We use argon to purge that environment so that we don't have additional reactions from oxygen just in the air. And we use that. We also are able to use the walls of that chamber to contain and intensify the duration of that reaction that we have. Some of the first uses of detonation synthesis were detonation nanodiamond, because carbon is obviously one of the free things that we have that we can use to react, and why we're trying to make silicon carbide and react with that. So our detonation here with the sort of temperatures and pressures that we are looking at is going to result mostly into diamond. We have varying pressures within that, so we're getting some sort of mix between amorphous carbon and diamond. But our main goal here, rather than creating just nano diamond, is to dope the explosives with other inner additives so that we can make silicon carbide that are frequently used in brake rotors, try and make silicon nitride, and other high temperature and strong nanomaterials that are difficult to manufacture or expensive to manufacture in other ways. This one really has three parameters that we can use, and it's what we are changing in order to alter what goes into those detonation products. So we can use these and understand detonation in general, as well as detonation synthesis specifically, and trying to determine what we work with. All of it is centered around the fact that we've got an exothermic reaction and a net release of energy. A few things here is the reaction enthalpy. With this, it's related primarily to the amount of energy that is released by an energetic material as it reacts. A greater reaction enthalpy is going to be more energy released overall, and change the amount of heat and pressure that we have within that environment, and determine where on that previous graph with liquid carbon and diamond we end up with the heat and pressure that we can have or that we use. Activation energy is the amount of energy we can apply to get the reaction started. If it's too sensitive, we can have accidental initiation. We try to avoid that as much as possible, but anything too insensitive, we might not be able to initiate it well. So adding even just too much inert additive is going to just change the propagation of that blast wave throughout, and whether we're actually able to maintain that detonation reaction throughout. And then finally, reaction rate or reaction progress. This is going to dictate the time which the explosive releases that energy. A fast reaction is going to release the energy before max expansion can occur. It's going to result in higher pressures and a more shattering effect from the explosive. We call that a brisant explosive. Something with a slower reaction process is going to more push the material and have a lower pressure over a longer duration as it expands throughout. So relating to this, something that we can visibly see, on the left we have a slow reaction progress, something we use as for blasting. We're wanting to essentially push the energy, have it in there longer, have gas expansion that enables that rock to expand and break and form that muck pile. And on the right, we have a much faster reaction progress, which is more shattering, and a quicker reaction there. This really is our chamber. There's a couple of students of mine setting up a test out at the mine in this chamber. You saw the explosive charge that we cast, so we can dope it with what we need. We're closing that and purging, and we get a detonation inside a closed vessel. And these are the detonation products that we're talking about. This is something you don't typically see when you're detonating something in air in a non-purged environment, but it's these products that we want to collect and process and purify and see what we end up with. And we get excited when we get soot, essentially, to many people probably. What's hard about this research area and any energetic research area is just the different scales that we have to look into to fully understand what's happening. I've shown you a lot of videos at this continuum or bulk scale where we're dealing with microseconds, milliseconds, and we can look at things like wave propagation and geometry. But in order to create some of these nanomaterials, we're really on the atomistic scale, and something that's really hard to measure and determine what's there. But detonation synthesis allows us to have that soot or that product at the end of it, and we can really start to see what's there. One way that we did this was using silica in different charges, and we had a shell around the explosive. We did this both through simulation and in the chamber to collect the detonation products. We had that silica throughout the charge, and we also had it in the center of a charge. And based on the temperatures and pressures, as we see these simulations run, this here is really just the CJ pressure of the explosive. And as we add those inert inclusions, we can see that we've got sort of little pockets of higher pressure and energy behind. and determine that, you know, the energy of the explosive or the CJ pressure of the actual explosive is not really telling us the full story as what's happening in those inner inclusions. And we can collect that, and we use silica so that we could look at the amorphous and crystalline content differences before and after loading in different areas, so we can begin to understand this better, and really improve the understanding of the relationship between detonation physics and chemistry, and material synthesis. So, summary, I've spoken a little bit about some of the topics that I've enjoyed working on here, and hopefully relevant to some of you as we go through and talk about those. But rather than a summary, I feel like this and topics like this are also the future of, you know, research here and other places. These topics, to me, the fighter jet canopy ejection really is, you know, it's an investigation by intrigue and of scientific theory, debate between students, and the use of facilities that were developed here to actually just go out and test these and find the answer to some of it. Traumatic brain injury is a response to a national need, and related to soldier health, and seeing opportunities that we can help with, and further our understanding as a whole through other collaborations. Coal dust explosion suppression, I included that really because it's only been possible because of the experimental mine and facilities that have been developed well before my time, and utilized something that was built for a specific purpose 40 years ago into a new purpose today, and different funding and opportunities. And then detonation synthesis, I just think it's a great example of unexpected collaborations and seeing opportunity in that through discussion, and making things happen. That's what's been so great about the last 6 years, is actually being able to just make things happen. I couldn't have this without, these are all my grad students and some undergrad over the last 6 years that I've been here. A lot of these are their initial ideas and thoughts, and we work together to make them that reality. So I definitely appreciate them and the work that they do, and new students, and the work we do here is what we need. And then really finally, I promise, I couldn't talk about or do a presentation called Having a Blast with Explosives without mentioning probably one of my favorite days here, and that was when Ozzie Osbourne came to visit. So one of my favorite things that hopefully you'll hear in the video is that every time he pressed that button or detonated anything, he did the crazy train laugh. So I definitely appreciated that. So we of course slowed that down. This is detonating Chord, the same stuff we spoke about earlier with the fighter jet canopy ejection. So we used our high speed for that. It was a Phantom V 2012. And then this final picture is with a cell phone. They have come a long way. But I wanted to share and reminisce on some of that too. So with that, I would be more than happy to answer any questions that you might have.
Thank you, Dr. Johnson. We do have some questions that have come in. All right, so I'm going to start here. What motivated you to get into explosives?
I'm probably one of the few people that doesn't have that story of when I was 10 and did something I probably shouldn't have in the backyard. I grew up in Cornwall in southern England or southwest England, and there's a lot of mining history there. There's a mining school there, and I just through geology and math, I got into that area, and then fell into the blasting side of things. And since here, you know, took opportunities when I saw them, and it's fun.
This next one is more of a comment. It says that she liked the nice tie-in to Top Gun. Poor Goose, she says, and she didn't know that was a real problem for fighter pilots. So that was Kind of tied with that question, we have one regarding the canopy ejection topic. Would you please re-explain what the difference was between what the existing fracture theory predicted and how you thought the fracturing worked?
Yeah, so with those two detonating chord lines that are parallel, I definitely think it's better. It worked better for us with the crack propagation. It is a better design. But the theory was that it would crack between those parallel lines. Whereas I thought, but that area is actually the full thickness as well of the canopy, whereas the way that it did break and the way that I thought that it would break was actually cracks to the surface where it's actually thinner. So that detonating chord is, we routed it. It was 1/2 inch thick plexi, and we routed about 1/4 inch and put that chord in between. So you actually only have 1/4 of an inch thickness to the base, whereas between you've both got a loss of energy and thicker material between, which is just harder to break in general. So essentially it just caused a crack between that 1/4 inch that was underneath the explosive.
Okay. Where do new explosives come from? The military, or are they secret for some period, or does S&T try developing new explosives?
There's constant development of new explosives. Most of it is related to trying to find something that is safer to use, so harder to initiate, but also have a faster reaction and more output. So they're really the two main goals that we are trying to achieve whenever you're trying to make a new explosive. And there's a lot of work at national labs and Army Research Office, Army Research Lab that are going into that. A lot of it starts with chemistry, math calculations. You're then getting into very small testing of sensitivity before you go into larger tests. So there are constant new developments. We don't really develop new explosives. We do, through things like the synthesis, mix current explosives in different ways, which I guess on paper is actually a new explosive when you're mixing energetics in a different way and you don't have an actual data sheet for it. But in terms of new explosives, we don't do research like that yet.
Do you work with companies like Controlled Demolition, Inc., and are their products trade secrets?
I don't really do a lot with demolition. We work a lot with industry in general. I showed you pictures of my current on-campus students or past on-campus research students, but we also have a lot of students that are through our distance program and online, and a lot of them come from companies like that and work with us there, but I don't particularly do research in that area.
Lately, much attention has been paid to the future of space travel, human expansion, and the utilization of resources beyond Earth. Out of your expertise, what challenges would you expect to overcome when using explosives in the weightless vacuum of space for mining purposes?
Well, you ended with it a little bit. Weightless vacuum, everything's going to react differently. I mean, even just water is going to boil differently here compared to, skiing in the mountains in Colorado, and we have a different reaction rate and pressure and temperature that we get at different rates there. So that's definitely a concern. Getting materials there is a concern safely. We're getting that to areas that have high energy and thrust output from space travel in itself, and how do we get energetic materials there safely, and hence more sensitive type materials. Another concern is just bulk of explosives needed if you're mining and using explosives to mine that way. It's 90% are used in mining by weight, but in terms of, you saw that comparison of the rock blasting compared to high explosive, the actual energy output is definitely not a 90-10 ratio. So you just need a lot more bulk to do something like that. So just getting things there, I can see a problem with.
All right, thank you. This next question is, what was Ozzie like in person?
Honestly, having him hang out with Kelly and Jack, it just reminded me of a family with their grandparent that was struggling to control. He was great. A lot of fun, and it just the whole family was just fun to be around and interact with, and they were just really genuine and down to earth. It was fun.
Sounds like it was a neat time. I think we have time for just one or two more. Question just came in. He says, very interesting and informative. He's always liked explosives. How did you get Ozzie to visit our campus?
It was probably something that I probably intended to say at one point. It really is just a great example of, how unique the explosives program is here, and how people like that have found us for that and want to visit for that. So it was part of Ozzie and Jack's World Detour show, and for this season they were driving from LA to Florida for one of his tours, and they were just finding things to do in the states along the way, and they got in touch with the university, and it kind of went from there. Yeah, I only was part of it a day, maybe two before, which is probably a good thing. Otherwise, I probably would have been too excited to be reasonable about it.
Great. This next question is regarding our Missouri S&T summer camp, our explosive summer camp. I don't know if many of our listeners tuning in know that at Missouri S&T we do have a summer explosives camp. And this question is, can an old alum, electrical engineering alum of 65 attend the explosive summer camp?
I have always wanted to do an adult camp. I think that it would sell. I think that if we should do bachelor parties, I feel like we could, make a lot of people happy by doing things like that. If you can't attend the camp, just get in touch and come out and visit anyway. But yeah, I've always thought about doing an adult camp quite seriously.
I think you would have a lot of attendees there. I hear a lot of people adults interested in the explosives camp.
Yeah.
All right, well, that wraps up our questions for today. Our winner of our random drawing is Kelly Williams. So Kelly, if you are still on, if you can drop your email into the chat or the Q&A box, we'll be able to get in contact with you about getting your prize pack. And then we just want to wrap up by thanking everyone for participating in today's lecture. Our next talk will be in September, and that talk will be hosted by Tom Yarbrough, one of our PhD students and a PhD candidate in civil engineering, and he'll be discussing batteries in the microgrid and solar houses. If you would like to learn about that talk or about any other talks that we will have on campus, I encourage you to go to our community page, which is community.mst.edu, where you can find this opportunity as well as many others. With that, I'd like to thank everyone for attending and participating, and we hope to see you in the future on our campus, perhaps at Explosives Camp. Have a good day.